Hi, folks. It's Jeremy. We talk a lot in our trainings and classrooms about making connections in mathematics. And I wanted to explore that more deeply today because I think it's very helpful in our instruction and our understanding of what we're trying to do in our curricula and our instruction, our teaching. And so I wanted to start at the beginning, right, which is thinking about what our goals are, right? When we think about teaching conceptually, right, for meaning and for rigor, and to ensure that kids are exposed to the kind of problems that make them think and actually require them to think on their own, we want to sort of ask ourselves, why are we doing that, right? Like, so what are our goals in teaching math conceptually? Well, one is that we want to have kids make meaning, right? Things should make sense for a lot of reasons, right? Not just in a logical sense, but also because we should be asking kids to do things and to solve problems and to figure things out that are meaningful, right? That cause them to understand what they're doing and they're not just doing it because someone told them to do it, right? I think the second piece that we're looking for is that we want them to be able to think critically, right? So critical thinking is our second goal. We want them to look at situations and not just try to find an answer, but really analyze what's happening and think about the best way to do something, or even what the task itself or the goal or the assignment or the essay or the project is asking them to do and why it's asking them to do it, right? So that's a second goal, right? Third, we really want kids to make meaningful connections. I think that's really connected closely to number one, but we want kids to live in a world and think in such a way that things are connected to each other, right? That things make sense in their world, right? So that they can then apply things, right? Connections allows you to apply what you've learned into the real world or into future learning, either way. And then, of course, what we're also looking for in conceptual based math classrooms is for kids to achieve, right? To achieve on rigorous assessments at the highest level, right? Whether those are formal or informal, right? So I want to talk a little bit today about how to achieve those goals, right? How to make meaning, how to make connections, how to do, have kids develop critical thinking skills, and ultimately to achieve in whatever they put their mind to. So let's talk for a second about how to help kids achieve those goals. The ways that we do that in a conceptual and rigorous math curriculum is to ensure that the tasks that we're asking kids to do are cognitively demanding, and in the way that we deliver those tasks or facilitate or teach those tasks, that we keep the demand cognitively high, right? So this credit goes to Mary Kay Stein and her team in the book Standards-Based Math Instructions, the casebook for professional development. They look at tasks through the lens of cognitive demand. And so there's different levels, right? On the top two, right, in this quadrant, you'll see that there are higher level demand tasks. And at the bottom, you'll see that there are lower level demand, right? Some of these might sound familiar because they sound a little bit like Bloom's taxonomy, but memorization tasks that require memorization, such as what is the formula for area, as a quick example, right? They just ask kids to recall facts or definitions, right? So recall definitions is one hallmark of a memorization task, right? It does not also require kids to do a procedure or to figure something out, right? Or to make a connection to a concept, right? So we'll just say that memorization as a task by itself is not conceptual, or it's not, and it's not connected. Sorry. Now, slightly higher demand, but still on the lower level of cognitive demand, is procedures without connections. Now, procedures without connections, right, in math are things that are algorithmic, right? This is, for example, having two numbers stacked on top of each other, and the prompt for the task or the directions just says add or find the difference, right? So there's a suggestion that you're supposed to follow a particular procedure. I'll give you some more examples of this in a minute. But those procedures without connection tasks do not require explanation. Or, as it says in the name, it doesn't require connection. You don't have to prove your answers with anything else. It just really focuses on getting the right answer, right? So in that way, it's really focused on the answer. Now, as we move up into cognitively demanding tasks, or higher cognitive demand tasks and instruction, we're looking at first at procedures with connections. And as the name states, this is asking kids to use a procedure or a process that's broadly dictated to them, but the kids actually have to make the connections between that, right? So you're basically with procedures with connections, you're using a procedure to find connections and illustrate concepts, right? I'll give you an example in a moment, but that is a more demanding task where you might require multiple forms of proof, and you'll definitely require some sort of an explanation about why things worked, right? And at the highest level of cognitive demand is doing mathematics, right? These are non-algorithmic, tasks. They require complex thinking. And there's no pathway, there's no suggested pathway for how to solve it, but there are requirements for your proof or your explanation, right? So you're going to figure something out. It's not going to tell you how to do it, but you have to use math, multiple forms of mathematics, to prove how you know that you completed the task or solved the problem, right? So it is very cognitive demanding in that way, and it requires basically application and proof. So let's go through a couple examples of tasks that might fit into each one of those categories, right? So on the lower level demand piece, we'll talk about it just in one topic so you can see the difference in the tasks, right? But at the lowest level with memorization, right, at level 1, it might say, what is the formula for area? And you could think about what an acceptable answer to that question is, and it's not demanding, right? You just have to name the formula, right? The second level, procedures without connections, might present a very simple task, but it might be focused on the answer, and the procedure doesn't require you to make any connections. So, for example, calculate the area of a 7 centimeter by 2 centimeter rectangle. I was about to put a question mark. It's not, just telling you what to do, right? So I turn it into an exclamation point. So that is a lower demand task, right? Because it doesn't require proof, it doesn't require examples, it doesn't require an explanation. It really is just focused on using a procedure. In this case, the procedure is implied, which would just be multiplication. You could skip count, you could use the algorithm, you could use repeated addition in this case. But the procedure doesn't actually require you to make connections or explain your answer. Now, if we keep going in demand here, right, what we could look at is a procedures with connections question. Now, I might not be able to write everything here, but I'll say part of it and then I'll write some of it, right? So, for example, you might say for a task at this level, a rectangle has an area of 24 square units, right? Draw 3 different rectangles that could have this area and label their side lengths. Explain how you found the dimensions of each rectangle, right? So I'm just going to bullet it out, right? Which is, give the area, right? State 3 different rectangles, right, that have that area. And then explain, right, how you found the dimensions. So in that case, what we're looking at is there's a procedure that's suggested. It tells you what to do. Take this area, make 3 different rectangles, label the sides, right, and then explain, right? So it tells you exactly the process that you're going to use, but it demands connections, right? So the connections that it's demanding are, all right, use area, work backwards to find the factors, right, or the factor pair that's going to make that area, right? Find 3 different ways, and explain, right, how you found those, right? So you're obviously going to have to explain some relationship, right, between the area and the side lengths. Hopefully, even using inverse operations or some connection between multiplication and division, right? So now at the highest level, right, of the most cognitively demanding level, we're doing mathematics, right? So one of these tasks might actually integrate multiple types of mathematics, but are still related to this topic of area. So for example, we might ask a kid to investigate the relationship between the perimeter and area of rectangles, right? Start with a perimeter of 20 units, find another rectangle with the same perimeter but a different area, and then ask them to generalize, right? What's the dimensions of the rectangle with the greatest possible area for this perimeter, right? Lastly, you might ask them to explain what the relationship between perimeter and area are, right? So in this case, right, so we're going to say I'm going to write this out. So given perimeter, right, then we're asking them, that's 20, right? Find another rectangle right, with the same perimeter but a different area. And then we're asking them to generalize it, right, by saying, what are the dimensions of the greatest possible area for this perimeter, right? So we might even ask them to explain what the relationship is, as I mentioned. So this is complex, non-algorithmic thinking in which they actually have to apply some of the formulas connected to other kinds of math, right? So this is not just area, it's also perimeter, but also they need to be able to experiment with math. There's no algorithm or given pathway to figure out the ultimate and most challenging answer, right? So what are the dimensions of the rectangle with the greatest possible area for this perimeter? That's some serious doing of mathematics, right? And we can tell that it's cognitively demanding. It's supposed to be hard, right? So in summary, when we're thinking about these goals, right, of getting kids to make meaning, to do critical thinking, to make connections, and then apply what they're doing, the best thing that we can do for them is spend as much time as possible in our math classrooms doing tasks that are of higher cognitive demand, right? Now, it's not to say that memorization and procedures without connections aren't important. We have to know formulas. We need to know facts. We need to become fluent in things, right? But when we're thinking about when we want to spend the majority, the lion's share of our time, we need to keep it up here if we really want kids who are making connections, applying their mathematics, and doing some critical thinking, right? So let's talk a little bit about this idea of connections at a deeper level, all right? So a math classroom that is very rich in connections is very similar to what mathematicians do themselves, right? So when mathematicians are trying to prove theorems or solve problems, the only way that they can prove is by using multiple forms of mathematics to support their argument, right? You can't just say, you know, this is how I solved it, or here's my answer. You actually have to show how you found your answer using proofs, right? So when we're thinking about kids, right, younger kids in particular, in K to 8 or even K to 12, we want them to see the connections between the different types of mathematics that they're doing so that they can make meaning, they can critically think, and then they can apply, all right? So let's take an example and take it across the different models of math, right, that we can make connections across, all right? So these are, 4 categories, right, that we might see mathematics modeled in, right? So concrete and physical, right, like stuff, right? Things, rocks, let's say, or fish, right? A wall, a painting, if we go back to the area and perimeter conversation, we can use physical models to sort of demonstrate math principles or to have kids make connections, right? So these might be blocks or cubes or teddy bears in an early childhood math class. And they might be things that are more complex a little bit later on. Then there's graphical or pictorial, right? We've all heard about concrete, pictorial, abstract. This is related here, right? But graphical are pictures, drawings of math, right? And in the early years, those are actually just representations of the direct models that they make, the physical models, drawings of cubes, as a quick example. And later on, they become more and more abstract as models, right? So for example, something like a tape diagram, right? Or even a graph, right? A graph is a picture of mathematics, right? A sketch of the shape of a graph, right? An exponential growth, right? Versus linear growth. Those are pictures of mathematics, right? Or graphical representations of mathematics. And then we have verbal, right? You actually have to explain your thinking, right? And sometimes you explain it verbally and sometimes you write it down. And there's a special language to use in mathematics, right? So it's terminology, but it's also the ability to explain something in mathematical terms or to state it in different terms, right? 16 tens is the same as 160 ones. That's language that demonstrates a concept and allows kids to make connections, right? And then lastly, there's number and algebra, right? Those are connected things. They're mostly at the most abstract level, right? Algebra being, right, using symbols to find unknowns and systems, right, of equations, right? That is connected to number, right? And so when we think about moving from the most concrete all the way to the most abstract, we're getting to the land of symbols up here. And numbers are symbols, right, for quantities and values, right? So let's actually walk through an example here, right? So let's think about a task that is mathematically rigorous, right? That's cognitively demanding. I'm going to state the task. And we'll actually write it down here so that we have a reference point in our video. But let's say that, let's actually say 2 people are sharing 3 brownies. Yeah, so for our question is how many brownies will each person get? Now the task might have more criteria listed underneath on the paper, or the teacher might state the criteria for success, for meeting the criteria of the task out loud. But, let's say you had to prove your answer, right? Or prove and explain how you know your answer is correct, right? So let's talk about first what a concrete model of that might look like. Now, we could either use a representation of the brownie, that's a concrete model, or we could actually use brownies in this case. So I'm just going to draw these because I don't have any brownies with me right now. But if we're thinking about 2 individuals, right, you could stand up 2 individuals in the classroom, right? And I was sort of thinking about early childhood right now, even though this is a fairly complex problem, right? And then you're taking these brownies. I'm going to draw them in 3D just to sort of give you the sense that we are talking about something concrete and physical. And just draw the third one just a little offset here so we can have space to model it. All right. So in a concrete situation, right, we could solve this problem by saying, all right, we're going to give one, and you'd actually hand that brownie over to child A, right? That child has one now. You give that second brownie to child B, and then you'd actually take a knife, draw a little knife here, right? And you'd say, wow, we've got one brownie left, but there's not enough for each child to have a brownie or each person to have a brownie. I'm going to cut this one brownie into 2 equal pieces, all right? And I'm going to give this child that piece and this child that piece. Now, from a connection standpoint, if the child did that, right, if the child had a knife and we gave that child the 3 brownies to share amongst herself and a friend, right, they could show us initially that they understand the mathematics by doling out 1 whole brownie to each child and then cutting that last brownie into equal shares and giving each of those shares, right, so that the 2 students or the 2 children have the same amount. That's a concrete model of mathematics that is viable, right? But we don't know the depth at which the child understands it until they make connections, right? So let's skip over here to verbal for a second because we're going to make the connection as well. But if we think about a child making a verbal connection to this, we would think about their explanation, right? So a child might say in this situation, each child gets 1 whole brownie and 1 half brownie. You might push that child to actually prove, right, or actually state their answer in another way, and they might say each child gets 1.5 brownies. Now I wrote fractional notation there, but they could have just said 1.5 even if they didn't know fractional notation at that point. But so right now what we have is a connection being made, right? A connection between the concrete and physical act that the child did or saw done and the language that then serves as proof that they understood it. That child's making a very strong connection that is mathematically viable and sound, right? Now let's move on into the way that we might look at that graphically or pictorially. And I'm going to show it in a slightly different way just to illustrate a couple of things about how it connects to more abstract math. But let's say that the child thought of the problem in a very similar way and was looking to prove that each child got 1.5 brownies. So they do basically a set of unit fractions, right, or bar models here, right, where each bar represents 1. And then each child is representing the folks who are sharing it, right? And if we look at this really closely, a child might coordinate right away, pictorially, that there are 2 here and that each brownie could be split into 2 equal parts, right, into halves. And they might say, all right, if this is child A and this is child B, I'm going to label each one of them, right? Because if I go ahead and split all of the brownies that I have in half, I am positive that these 2 children are going to get the same amount, right? Because they coordinated the shares with the sharers beforehand, right? And so if that child understands that this is 1/2, this is 1/2, and this is 1/2, the child now has a pictorial model, right, that is proving that the student or showing that each student gets 1.5, right? Or 3 halves in this case. Now, if this child then matched it with language, now we have a viable explanation or answer, right? It would be great if the child was able to do all 3 of these things, show how they did it physically, draw a picture of it, and then say or write an explanation depending on what level of literacy that they were at. But now we get into the point of algebra and number, right, in a couple of different ways that we could start to express this relationship between the shares and the sharers, right, or this idea of division or multiplication, however the kid's thinking about it, right? So let's think about the different ways that we can make connections across these. Let's start with this one here, right? So if we think about it, right, what we're doing here is that we're saying, right, 1/2 plus 1/2 plus 1/2, right, equals 3 halves or 1.5, right? And then we also could say, all right, so those are 3 halves. If we add those 2 3 halves together, right, we get back up to our total, right, which is 3, right? Another way to think about it might be that we are doing 3, right, divided by 2, right? And a child might think about that as 3 halves, right? Which is very much matches this model, right? We've got 3 and we divided them by 2, right? And then if we start to stretch it even towards more sophisticated math, we can think about this as a ratio, right? So if we thought about it as 3 to 2, right? 3 brownies for every 2 children, we could find the value of that ratio, right? And the value of that ratio is 1.5 or 1.5, right? Lastly, if you wanted to start to sort of generalize this idea, right, of what's happening here and how fractions work and that fractions are division, you could get into algebraic statements, right, or expressions. So if we're thinking about this idea, right, where B is the shares and C is the sharers in this context, but you want to like generalize it, you could say that B divided by C is going to be B over C, right? And that is a ratio. The point that I'm trying to make here, right, that's really important is that if we want to have critical thinking students who are making meaning of the math that they're doing, right, that are problem solvers, that they're connection makers, and that they know how to apply what they learn in the math classroom, right, how to apply this formula or this thinking about ratios, or, you know, the fact that this could have been a multiplication number sentence, right? If we want them to apply those kind of things, right, we need to, one, present them with cognitively demanding tasks, right, where they're either doing procedures and making connections or actually doing mathematics, right? We need to know the difference between how those tasks are phrased, written, and how they're taught, right? Because there's a way to take away the cognitive demand by telling a child how to solve a problem, right? Which we don't want to do. We want to support them and guide them, but we don't want to tell them how to do it, right? We want to keep those rigorous tasks as the majority of our instruction, right? And we want to make sure that in the mathematics classroom that we require students to make connections across types of mathematics, right? Physical, graphical, verbal, right? And number and algebra, to be able to explain their answers so that we're sure that they really deeply understand what they're doing, right? That's how we're going to have rigorous mathematics classrooms, right? Thanks for listening. I hope it's helpful.